So in this video, I want to talk about some situations that sometimes arise when we are trying to evaluate limits. So we know that infinity over infinity, or 0 over 0, are indeterminate forms. And there's also some other ones too. These are just the ones I like to consider most of the time. But what about other situations that might arise with limits that involve 0 or infinity? So I just want to run through 3 examples to show you some other things that might happen so you can apply them when you're solving limit problems. So when we are evaluating limits, the first thing we like to do is substitute in the point that we are approaching. So if x is approaching a, we substitute in for a and see what we end up with. So in some cases, we're going to end up with things that aren't indeterminate forms, but are also some things that involve a little more interpretation. Okay, let's just jump into an example so you can see what I'm talking about. Let's say I am trying to evaluate the limit as x approaches 0 of 1 over x. So my technique is to substitute in x equals 0, so I'm getting 1 over 0. Now, 1 over 0, when we divide by 0, this is undefined, we can't do this, and it's not an indeterminate form, so I'm not getting a 0 over 0 or something with infinities. So we're going to need to interpret this in some other way. So when we divide by 0, as I mentioned, this is undefined, and so this actually just means that the limit does not exist. And we can write it all out, or we can abbreviate does not exist as DNE. So if you were given this problem, this is how you would solve it. You would substitute in 0, see that you are dividing by 0, but you don't have 0 in the numerator, so it's not a 0 over 0 situation, it's a 1 over 0. And so this tells you that the limit does not exist. Okay, let's do a slightly different example. This time, let's say I want to evaluate the limit as x approaches infinity of 1 over x. So instead of approaching 0, we're going off to infinity. You can think of going off on the right-hand side of the graph forever and ever. So here, if we were to think about substituting in infinity, we can't really substitute in infinity since infinity isn't a number we can plug in, but we can think about what happens as it goes to infinity. Here we would be doing 1 divided by some number that's getting bigger and bigger and bigger. So we have a 1 over infinity. This isn't an indeterminate form either. It's not infinity over infinity. So we're going to need to interpret this a little bit. If we think about a fraction and we're doing 1 divided by a number that gets bigger and bigger, maybe we have 1/10th, then 1/100th, then 1/1000th. As the denominator gets bigger and bigger, the fraction is getting smaller. And as it gets smaller, it's actually getting closer to 0. So as the denominator goes to infinity, the entire fraction is going to approach 0, since we're dividing into more and more pieces each time. You can imagine if we had 1 pizza and we just kept dividing it into pieces over and over and over again, increasing the number of pieces we did, we'd eventually have pieces that were basically had no size. The pieces would get smaller and smaller indefinitely. So this is not an indeterminate form, but it does have a solution, and that solution is 0. And since both of these examples include 1 over x, it can be sometimes helpful just to remind yourself of what the graph of 1 over x looks like. I'll just sketch it here really quickly. Basically, it has 2 pieces, one on the left-hand side and one on the right-hand side, and it has a vertical asymptote at 0, so at that 0 value, it's undefined. But as we approach infinity, thinking about what happens as we go to the right, we're approaching 0. So 0 is the limit as we approach infinity. Alright, I just want to do one more example that looks similar to this. So we've done 1 over 0 situations and 1 over infinity situations. But let's try one more thing. So here I'm looking at the reciprocal of what we did last time. So I'm still doing the limit as x approaches infinity, but I'm going to do x over 1, which you can really just think of as x. I just wrote it as x over 1 to link it back to that previous example. So here, as we substitute in infinity, or really as we think about what happens as we approach infinity, I'm getting infinity over 1, which is really just infinity. So we're sort of getting that the limit is infinity, but infinity isn't really a number, it's not a value we can point to, so this means that the limit does not exist. And again, we can think about the graph of this as well to help us out. So I'm really just looking at what happens to the graph of x, which is like y equals x, as x approaches infinity. So y equals x is a linear function that passes through the origin. It has a slope of 1. And as we go to infinity on the x, that means going to the right on the x, the y value just continues on and on without bound. So The limit does not exist since the graph will just continue going forever and ever. It's not reaching any sort of limit or highest value. So, to summarize, we have our indeterminate forms infinity over infinity or 0 over 0. And when we have these indeterminate forms, we can use L'Hopital's rule. But we can also encounter other situations, as we just saw in those examples. So something that might happen is we substitute in the value and we end up with a number divided by 0. So when we have a number divided by 0, this limit does not exist. And this is really just because we can't divide by 0. The next case is that we have a number divided by infinity. In these cases, since we are dividing by something that's getting larger and larger, the fraction is getting smaller and smaller, and so this limit would be 0. Then the last situation that we talked about was infinity over a number, and when we have infinity as our limit, this also does not exist. In some cases, when we have a limit that does not exist, we might want to provide more information about like if it's approaching positive or negative infinity, but what I want to just communicate in this video is that you just need to know that it does not exist. Okay, and those are the situations that might come up. Just keep an eye out for these as you are doing limit problems, and don't forget to check for an indeterminate form, like infinity over infinity or 0 over 0, before you start using L'Hopital's rule. Otherwise, straightforward substitution should get you the answer, or you might have one of these three cases we talked about where you have 0 or does not exist. Okay, and I just have one more reminder for you that I want to talk through in case it comes up. So let's say you're taking the limit as x approaches a of some constant. It could be any constant, it could be 5, negative pi, 1/2, a million, just some constant. The limit, since it has no x's involved in it, there's nothing there to substitute in, the solution to the limit is just the constant itself. The limit as x approaches anything of a constant c is just equal to c. Alright, that is it for this video with just a few reminders. Thanks so much for watching, and I will talk to you in the next one.